Welcome to this explainer. Today, we're unpacking a massive shift in how we approach our university's digital future, specifically transitioning from reactive firewalls to proactive machine learning. Look, higher education is facing an unprecedented threat landscape right now. So if you're an administrator or an IT leader tasked with protecting our institutional data, this briefing is definitely for you. We're going to dig into some recent localized research on network intrusion detection to figure out exactly how we can build a robust, proactive defense system for our campus, and we'll outline the actual steps needed to deploy these clustering tools right within our network. Let's start with a pretty jarring reality. Over 60% of successful cyber breaches globally involve new, previously unrecorded attack variants. In the cybersecurity world, we call these zero-day attacks. They are completely novel. They don't match any known malicious patterns. And think about the real-world consequences of that number for a university. A successful breach isn't just a temporary IT headache. It means ransomware potentially shutting down the admissions portal during enrollment week. It means decades of sensitive academic research data being held hostage, or thousands of student financial records just out there, exposed. The cost of inaction, the stakes for our institutional data, have literally never been higher. And that brings us to a critical question for our administration. If an attack doesn't have a known signature, are we completely blind to it? A university network is incredibly diverse, which makes defending it a really unique challenge. We've got students logging in from dorms on their personal laptops, faculty pulling sensitive research data from off-campus servers, and staff handling secure financial records every single day. If our defense relies solely on blocking what we've already seen in the past, our academic IP and our students' personal records are basically sitting ducks for the threats of tomorrow. Okay, so here is our roadmap. We're going to quickly cover the campus security crisis, why traditional firewalls fail, proactive defense through clustering, deploying the pipeline, and finally, securing our institutional future. Let's dive right in. Section 1. The campus security crisis. Moving right along to Section 2. Why traditional firewalls fail. To understand where our legacy systems fall short, we really have to look at our complex environment. Our campus network is full of heterogeneous devices and totally unpredictable user behaviors, creating a massive surface area for both external and insider threats. What we need is a vital paradigm shift, moving away from a reactive blacklist approach toward a proactive behavioral analyst model. Think about traditional firewalls. They use signature-based detection. They literally act like a bouncer at a club holding a blacklist. If an attacker's name is on the list, boom, they're blocked. But if they're wearing a disguise or if they're a brand new zero-day threat, that bouncer lets them walk right through the front door. Anomaly-based detection, on the other hand, is like a highly trained security guard. A security guard doesn't need constant, expensive list updates. They just adapt to the environment. They know what normal campus activity looks like, and they immediately flag anyone acting suspiciously. They catch unknown threats before they ever have the chance to strike. Which brings us to Section 3, proactive defense through clustering. So how do we practically implement this anomaly-based approach? Well, what's absolutely fascinating in the research is this focus on clustering. It's an unsupervised machine learning process that groups similar data points into discrete categories, and it does this without needing expensive pre-labeled training datasets. Now, that word unsupervised is incredibly important for us as administrators. It means we don't have to burn thousands of hours and huge chunks of our IT budget manually labeling malicious traffic just to teach the software what to look for. It naturally finds the hidden structures in our network traffic entirely on its own. It autonomously learns what normal traffic looks like on our specific campus network. It essentially turns that security guard into a customized, non-stop expert for our institution. The first major tool in this arsenal is the K-means algorithm. This method partitions data to quickly catch dense, high-volume threats that might try to bombard our campus servers. The way it works is by mathematically finding central points, called centroids, and grouping data right around them. Think of it like suddenly spotting a massive crowd rushing the registrar's portal during course registration, but driven by a malicious botnet instead of actual students. When a huge denial of service attack hits, it creates a tight, highly visible cluster of abnormal traffic. K-means operates incredibly efficiently to isolate that dense spike instantly, catching those brute force attacks rapidly before they can crash our critical academic systems. On the flip side, we employ a second algorithm called DBSCAN. Its density-based logic is perfectly suited to isolate network noise. See, instead of looking for big, round clusters like K-means, DBSCAN looks at the density of connections. Let's put this into a specific administrative context. Say a compromised student account suddenly starts downloading gigabytes of financial aid data at 3 a.m. It's just floating out there in the middle of nowhere, way outside our normal student and staff traffic patterns. DBSCAN catches that. It flags that sparse outlier as noise. This makes it an absolute trap for low and slow, stealthy insider threats that are trying to blend in or exfiltrate our institutional data byte by byte. And we know this works because of rigorous testing against the NSL KDD benchmark, which is basically the gold standard in cybersecurity research. This testing ensures our tools catch the full spectrum of threats. Let's really look at the sheer volume differences here. Denial of service attacks. They are loud. They make up over 36% of anomalous traffic right at the top. Those are the high-volume server crashing events that K-means handles beautifully. Then you have probing attacks at about 9%, representing network surveillance, and remote to local at around 0.8%, which is attackers trying to guess passwords. But look all the way down at the bottom row. User to root, or U2R attacks. They make up a tiny fraction of a percent of network traffic, literally 0.04%. Yet, they represent a deep internal compromise of our systems. They are the ultimate needle in the haystack that a traditional firewall entirely misses. But our clustering duo? It catches them. While K-means handles the massive, loud attacks, DBSCAN excels at catching those incredibly rare, highly dangerous U2R anomalies. Together, they give us the whole shebang. Totally comprehensive coverage. Okay, Section 4, Deploying the Defense Pipeline. Now you might be thinking, this all sounds great, but deploying advanced machine learning is going to require an expensive server farm, right? Actually, no. The research shows this entire deployment pipeline operates incredibly smoothly on just a quad-core CPU and 8 GB of RAM. To put that into perspective, that is the processing power of a standard-issue Office laptop. We achieve this highly streamlined, cost-effective pipeline through careful data normalization and dimensionality reduction. And dimensionality reduction essentially just means simplifying the data without losing its meaning or its critical features. By cutting out all those unnecessary variables, we can process network traffic intelligently and deploy these clustering tools right within our campus network without needing massive budget-breaking hardware investments. Looking at the workflow itself, it proves we have a fully architected, ready-to-build system. Notice the fork-join structure at the center of the pipeline. The system doesn't make you choose between K-means or DBSCAN. It actually runs the network data through both branches at the exact same time. By evaluating multiple machine learning paths simultaneously, we make sure we don't put all our eggs in one algorithmic basket. It then joins those results together at the end to give our IT staff the highest overall detection accuracy. It's a complete, end-to-end blueprint designed specifically for high-efficiency threat detection. And because the whole thing is built on a modular, layered architecture, our administrators can easily upgrade analytical components in the future. I really want to put some extra emphasis on this. This upgrading can be done without disrupting the entire university network. Say a much better machine learning algorithm is invented 5 years from now. Well, our IT team can simply slide it right into the model layer without having to rebuild the data layer or the presentation layer from scratch. It completely future-proofs our security investment, and crucially, it prevents the kind of costly downtime that disrupts online classes and vital campus operations. Finally, Section 5, Securing Our Institutional Future. The research leaves us with this quote: "Implementing an autonomous anomaly-based detection system is a critical necessity for maintaining the integrity of the institution's digital infrastructure." That powerful conclusion really highlights the true stakes of our conversation today. Upgrading our security just isn't a standard IT task anymore. This isn't just about running a software update. It is absolutely about maintaining the fundamental trust that students and faculty place in our digital infrastructure. It's a vital mandate to protect our academic IP, our student records, and our overall institutional reputation. We're shifting the mindset from merely maintaining servers to strategically defending the very lifeblood of the university. So, I'll leave you with this final thought. When the next zero-day threat targets higher education, can we really afford to wait around for someone else to write the signature? Or will we choose to be proactive today? Adopting anomaly-based clustering gives our campus the autonomous, intelligent defense it frankly deserves. Thank you so much for joining me for this explainer, and I hope this gives you a very clear vision of what our institutional defense can and should look like moving forward.